Hello, statistics students. Welcome to this video on the linear regression model, components of the model. A statistical model is a set of features that we expect our data to have. The closer our model fits reality, the better will be our inference from the model to reality. An important statistical skill is to determine how well the data fit the model. The adage garbage in, garbage out applies. If we don't have a good agreement between model and reality, then we won't make useful inferences about reality. Recall from chapter 4 that the regression line is a method used to summarize the association between two numerical variables. In chapter 4, we required only that the association be linear. This was all that was needed for us to summarize, describe, and make predictions about associations via the regression line. Requiring linearity remains the most important condition of the model in this chapter. If the trend is not linear, then our estimates and predictions will be biased, perhaps severely biased. Looking back, describing associations. In chapter 4, you learned that in describing associations, you should examine the trend, positive, negative, non-existent, strength. Strong trends have little vertical scatter, and shape, linear or nonlinear trend, and report them in the context of the data. That's what we did back in chapter 4. However, we now wish to do more than simply describe an association between variables. We now want to be able to measure our uncertainty in making predictions so that we can make inferences about the population. The first step is to provide a statistical model that describes this uncertainty. With this model, we can then quantify our uncertainty by calculating margins of errors for confidence intervals and p-values for hypothesis tests. Conceptually, the model tells us how the data were generated. This generation happens in a two-step procedure. Number 1, for a given value of the predictor variable, a straight line equation determines what the value of the response variable should be. Number 2, next, some random noise is added that results in the observed value of the response variable falling a bit above or below the line. Again, number 1, for a given value of the predictor variable, a straight line equation determines what the value of the response variable should be. The first step is often called the deterministic component of the model. Deterministic because it says, this is the real shape that determines which observations we shall see. For all of the models in this text, the deterministic component is always a straight line. Number 2, next, some random noise is added that results in the observed value of the response variable falling a bit above or below the line. The second step is called the random component. The random component acknowledges that, even though the deterministic step might be the true structure of the association, randomness also appears that partially hides this structure. This randomness creates uncertainty in our inference. The random component tells us what that uncertainty looks like. To illustrate how the model generates data, let's say we have selected 4 books of different lengths. We know the total number of pages in each book exactly because we can just open the book and look at the final page number. These numbers are 203, 317, 409, and 765 pages. We will exploit what we learned in chapter 4 about the relation between page numbers and width of books. From chapter 4, we got a regression line based on a sample of 24 books, and it says that the width of a book in millimeters should be the predicted value is 6.22 plus 0.0366 times the number of pages. So we're using the number of pages to predict the width of the book. This is the deterministic component of our model. The deterministic component tells us that our 203-page book should be, we take 203 multiplied by 0.0366 and add it to 6.22. And our model says that a book with 203 pages should be 13.6498 millimeters wide. For our 4 books, for all of the books, 203, 317, 409, and 765, their predicted width is given in this table. We just calculated for 203 that it should be 13.6498 or 13.6. We've calculated for each of those, 317, 409, 765. We can see these points on our line. Number 2, and statistics as in real life. What should happen is rarely what does happen. To account for this, the random component of the model adds random noise to these widths. Instead of a book with width 13.6 millimeters, we see 13.6 millimeters plus or minus some random amount. We could simulate this observed width with a random number generator on a computer. We would instruct the computer to draw a number line from a normal distribution with mean 0 and standard deviation of, say, 5 millimeters. The value we actually observe then is the deterministic value, 13.6, plus this random amount. If this random amount is positive, then the book we see is wider than the expected width. In this case, the observation will be above the regression line on a scatter plot. If the amount is negative, then the book is narrower than what we expected, and the observation will fall below the regression line. And you can see these random amounts plotted in B. The second step adds random noise, which moves each point slightly above if the random amount was positive, or below the line if the random amount was negative. And this concludes this video on the linear regression model, components of the model.